Now I don't know yet whether I will create a course based on this book or not, but I have a whole book here on the Universal Turing Machine, UTM, a collection of essays. So the Universal Turing Machine, and subtitle, A Half-Century Survey, and some of the contributors to, so it's about nearly 30 essays. Well, one's by Hodges. He's the famous biographer of Turing. He really put Turing on the map after his biography came out, I think in the 80s. Who else is big names here? Martin Davis. I'll be doing courses on 2 of his books, 2 courses on his stuff. Bennett, Charles Bennett. He's rather famous in the field of quantum computing. Chayton. He's a sort of modern Turing, or a modern Gödel. People often equate him as a kind of triangle. He's the 3rd member of the triangle. So Gödel, and then in time sequence. So Gödel, Turing, Chayton. Now, I have a lot of books by him, and he's done something that puts him in that category with those 2 other famous names. So I mean, I haven't included those courses as my core courses, but I would like, at some stage, if I can live long enough, I plan to give a course or 2 on Chayton's work. Who else? Martin Davis again. Penrose, Sir Roger Penrose, on the physics and mathematics of thought. Interesting question. I'm toying with the idea also of giving a course on the relevance of Gödel's theorem, incompleteness theorem, to the human mind. Like, is the human mind a machine? Is the human mind superior to a Turing machine? Is it super Turing or not? Stuff like that. Really, really interesting questions. Okay, well, the rest not so well known. All right, now about like I was saying in the first session, the proof that the language where is it? Here. The proof that language is in fact oh, you can't see it. I keep forgetting. The proof that A suffix tm is undecidable, it involves the use of something called the diagonalization method, which, as I was saying, was invented by Cantor well over a century ago now. Mathematician, German I think he was. He ended up going insane. Well, as I was saying in the earlier session, so he was concerned with trying to think about the sizes, relative sizes, I guess, of infinite sets. So a lot of people derided him, saying, no, you have the wrong conception of infinity, and a lot of mathematicians intensely disliked what Cantor was trying to do. Now, Hilbert loved what Cantor was doing. So there's a lot of mixed opinion. So basically what Cantor was trying to show was comparing sizes of sets. Now, if you have 2 sets that are finite, well, it's easy to compare their sizes. You just simply count the number of elements in the 2 sets. So say you have set A and B and they're both finite. Well, then you just find mod A, like A in the vertical, 2 vertical bars, and by definition, the size of a set is just simply the number of elements it has. Okay, so you just count the number of elements, and you do that for set B as well. So vertical bar or mod, the size of B, and the A or B, the one that has more elements in it is larger. You know, that's trivial, no problem. But how would you compare the size of two infinite sets, A and B, or C and D? That's not so obvious. Well, Cantor thought about this. He was interested in this problem because he had this intuitive sense that some kinds of sets were a different kind of infinity. Yeah, to start with, there are two kinds of infinite sets, and he felt, his intuition was that one kind was a sort of, in a sense, a smaller kind of infinite set, and the other one was larger. And then eventually he went on and, via this diagonalization method, he actually proved that the larger type of infinity set exists. And then he generalized that and did a whole new kind, created a whole new mathematics. And I will give a course on that, probably at Masters 1, M1 level. And I'm becoming increasingly conscious of choosing textbooks that are not too thick. So this one, well, here's my finger, you can get a sense of the size. It's about the same width as my finger. So it's only 100 all the index. It's only about 130 pages. And here's the theory of sets and transfinite numbers. Okay. So I will give probably an M1 level course on that. Now notice the term transfinite. That term is stuck, but I think it was, well, I'm not sure. One thing I'm a bit weak on is the history of mathematics. That I can guess that there was so much flack, so much criticism, that Cantor was getting from his colleagues. So instead of using the word infinite in his titles and papers, he chose to use this more, euphemistic, watered down term instead of infinite sets, because you have to mention the word infinite, and that's like a red flag to a bull to a lot of his mathematical colleagues. So transfinite, beyond finite, which is just infinite, right? So anyway, but the term stuck. So the topic is transfinite numbers, which is just infinite numbers, and there's a whole category of them, right? And there's a whole arithmetic. So I guess one of the real novelties that Cantor brought into mathematics was treating infinities as a kind of number that you could manipulate, like other numbers. And it was that idea that a lot of mathematicians strongly objected to. They said, "Oh no, infinity is more a process." And there's a lot of discussion on the nature, almost the meta mathematics. What is infinity? What's the nature of infinite sets and whatnot? Anyway, so it's transfinite numbers, like the Alephes, the various kinds of infinities, finite cardinal numbers, multiplication of ordinal numbers, transfinite induction. So the arithmetic of cardinal numbers, countable sets. Right. So I'll do a master's level course on that. Okay, so the diagonalization method itself. So let's start with a basic question. You mentioned your Cantor. You're trying to find a way. How can you take two infinite sets and come to the conclusion that one is larger than the other? Now, obviously, you can't just count the